So, welcome. Good morning, everyone. Sorry for this delay, technical questions. So, good morning. Welcome, everyone, to the 7th PYCHeM. I'm Maria Inês Dias. I'm here. I'm Maria Inês Dias. I'm here in representation of the organizing committee, and I will be the chair of this opening ceremony. It's a pleasure for all of us that this moment has finally arrived. We have been waiting for more than 1 year for this event to happen. It would be our pleasure to have you all here in Bragança. It would have been a great opportunity for those who have never been here to get to know our city and our institute, but I'm sure that more opportunities will arise in the future. However, despite being an online Congress, the program has a high scientific quality, it's very diverse, and we hope that everyone can make the most of it. For this opening ceremony, I want to thank the presence of the Honorable President of the Polytechnic Institute of Bragança, Professor Orlando Rodrigues, and also the Honorable President of the Portuguese Chemical Society, Professor Artur Silva. Thank you for being here with us, and without further ado, I pass the word to Professor Orlando.
Hello, good morning to everyone. Good morning, Maria Inês. Thank you very much. Special compliment to Professor Artur Silva, President of the Portuguese Chemistry Society, and all the participants in this Congress. Just a few words to, first of all, to thank you all for participating in this event. Unfortunately, it will be not possible to do that in a presential way as we want, and it was the first intention, but we are used to working this way, and thank you very much for all of you for participating in this Congress, especially for the guests that will do an important job in the Congress. Thank you very much for the Portuguese Chemistry Society to choose Polytechnic of Bragança to this 7th Congress of the young Portuguese chemists. And a word to also to thank these so dynamic young people that work so hard in doing these events. Fortunately, we have a very good team in IPV, in the Polytechnic Institute of Bragança, working in these fields. And for sure, chemistry and related science, it will be in the center of the global challenges that we will face in the future. For sure, we will have very important challenges in the domain, for example, of the energy, of natural resources, food, and in all of these very important global challenges that we will face in the next future, chemistry for sure will be in the center, and we will need a lot this kind of science to face this so important challenge. And for sure, it will be a privilege for a scientific society to have a so dynamic group of young scientists, and this will reveal the vitality of this discipline, because having this so important group of young scientists, is a privilege for sure. So thank you very much, all of you, for doing this in so dynamic and putting so much energy on that. Thank you very much.
Thank you so much, Professor Orlando, for your kind words. We share every thought that you talked about. Thank you so much. We move on to Professor Artur now. Professor, it's your turn.
Good morning to all of you. The first compliment it will be for the president of the Instituto Politécnico de Bragança, Orlando Rodrigues. Thank you very much for receiving in the institute. It's a way to say that receiving in the institute because today it's only to in this way, but well, to receiving this special event in your institution. It is always a pleasure to have the collaboration from the Portuguese Chemical Society and the Instituto Politécnico de Bragança, because it's not the first time that we were there with other events. The second compliment it will be for the organizing committee, because it was hard times. We have to postpone the first date. We are facing strange times, and but even so, we even in these conditions we reached to organize the event. And it's an excellent event in terms of the speakers that we will have. It is, I think it's always this type of events, and in this special case for the young chemists, it's a way to present the work that the people are doing, and to discuss. Of course, that the discussion of the posters and other, it will be more not in the normal way. It will be more tough, more complicated. But I think at the end of this event, we will be more rich because we were there. We were presenting the work and discuss with other colleagues. Of course, that this organization will have also for the first time a special contest, the retrosynthetic contest, that it will be the end. It will be on next Friday. It's the first time that we are organizing this, but I think it will be also the opportunity to see the young chemists to prove the quality of the organic and medicinal chemists that we have, and it's one way that we will see on next Friday. I need also to highlight to all the presenters in this event that the Portuguese Chemical Society, as you know, have a lot of divisions and groups. The society are also responsible for participating in international organizations, to organize national and international conferences, are responsible also for the students in chemistry Olympiads, in different Olympiads, the Portuguese, the international, the Ibero-Americans, also for stimulate research with some prizes. But we are also we are also owners of the Chems Europe, that it was in the former times it was ChemPubSoc Europe, that has its European Chemical Society publishing, where we have a lot of journals. And I ask you to think about, when you publish your works, to publish in that journals, because it's one way to help the Portuguese Chemical Society, because we are owner of this. We need to push these our journals to have better quality in terms of publications, to have more better impact factors. So I ask you, to all of you, to think in our journals. We have a great numbers of journals cover all the branches of chemistry, and it's a way to publish our works in the journals that the Portuguese Chemical Society are also co-owner of this Chems Europe Society. So after these words, I will wish a very fruitful and a very nice Congress, and I will meet you on Friday, and at least on Friday during the retrosynthetic event, and also in the closing ceremony, at least. Ines, I wish you to you and to all the organization, because it's always a different way to organize this event with computers, with we don't know how many people are in the other way.
We lost we lost the sound of Professor.
Condition.
Okay.
Yes, and hoping that at the end you will be happy to have organized this event, and all the colleagues that attend the event will be more rich and happy to be to. Thank you very much.
Thank you, Professor Artur, for your kind words. It's always good to have a validation of from that side. It's very good. We are truly excited for finally have the opportunity to organize the event. It's been more than 1 year. It's like we feel like we have organized 2 events, because we have already everything ready for last year, and then we have to cancel everything, and now again, and in different conditions that we think. But I think it will be very good. We have a good program, and like Professor Artur said, we have the Retrosynthesis Award. We have several things that are not normal to be in a congress like this. So we will see you there in the Retrosynthesis Award as a jury member of the award. So thank you so much. And for the publication of the work, the Química, from SPK, will give the opportunity for all of the participants of the Congress to publish their work if they want after this Congress as a mini manuscript, as a mini paper manuscript in the Química newspaper. So thank you so much for your presence here. Thank you so much to Professor Orlando. We are very proud that you validate our work, that you validate this Congress. So thank you so much. We will see you in another time, and let's move on to the scientific program. Thank you so much. So for those of you who are watching now, thank you again for joining us. Before closing this session, just 2 reminders. If you want to ask questions, you can put them on the comment section of the live streaming on YouTube. Also, as most of you know, we will give 3 best poster awards. Okay, so to vote on the best poster, on the 3 best posters, you can go to the Congress website, and there they are listed. The e-poster communications are listed in and divided by fields of expertise. Okay, so you can vote there. You have a Google web sheet that you can filled in with your participant number that is also in the website, and then you can choose the 3 best posters. That's it for my part. I now conclude the opening session. Thank you again to our distinguished guests. Now we can move on to the first scientific session, moderated by Dr. Susana Cardoso. Dr. Susana, we have already here Dr. Neil Champions. So let's move on to Dr. Susana. Thank you so much. Thank you again. And we will see you in the last day of the Congress. Thank you, guys. Enjoy the Congress. Dr. Susana, it's up to you.
Inês, hi. Inês, we can move on, but it's not still, it was programmed for 10 o'clock. Maybe we should wait for a minute, for some minutes. Do you think? It's better,
yes.
No?
Yeah,
so
yeah.
let's wait for a few minutes.
Yeah, while we wait, we can post a promotional video of our city.
Good.
So
good choice.
in
yes.
in these last minutes before 10 o'clock, we can post the video. So we will.
Okay.
Okay. Let's share the screen. Here, share the screen, and now I think I have to change the microphone.
Em criança, tudo é novo e cheio de magia. Olhamos para o passado. Imaginamos o futuro. Por entre estas pedras milenares, semeei sonhos. Esta é minha terra, Bragança. Quanto do que nos tornamos vem de onde crescemos. Tantas foram as pequenas coisas que nos fizeram quem somos, sem sequer nos apercebermos. Há algo que me chama, que me faz ir mais longe. Uns chamam-lhe loucura, eu chamo-lhe aventura. Os sabores intensos desta região são um espelho das suas gentes e da sua cultura. Sabores requintados que me enchem o coração. Tantas histórias se escreveram por estes caminhos. Hoje eu escrevo a minha própria história. O que vejo, o que toco e o que sinto. É isto que eu quero partilhar. O vento trouxe-me até aqui, onde o efêmero coabita com o eterno, onde o granito e o xisto abrigam flores e sorrisos. Vai e vê por ti mesmo, dizem-me. Ouve a terra e contempla os céus. De olhos postos nas estrelas, sinto-me pequeno e grande ao mesmo tempo. Porque quando fecho os olhos, sei que sou do tamanho de tudo o que vivi. Há um lugar onde criamos memórias que perduram para sempre. Bragança, naturalmente.
So I hope you guys like it and that this small promotional video of our city, Bragança, can sharpen your curiosity and motivate you to come meet the city, come visit, come and enjoy the little pleasures of our region, Trás-os-Montes. So now we can move on to the scientific program. Dr. Susanna, I will move on to you. Thank you so much.
Thank you, Inês. So good morning to all. And so as Inês told, we are now starting the scientific part of the conference. And this will start with the first of two plenary sections. This first section or lecture is entitled as Molecular Organization, a Journey Through Complex Structures, will be delivered by Professor Neil Shemnis, who I'm pleased to present. Thank you, Professor. Professor Neil Champness is a professor of chemical nanoscience at the University of Nottingham, UK. His research covers chemical nanoscience and molecular organization, particularly focused on molecular design and synthetic methods, employing self-assembly to create framework materials on surfaces and in the solid state, and for the creation of interlocked structures in solutions. His work has been recognized with several prizes from the Royal Society of Chemistry, and in 2011, he was identified as one of the top 100 most cited chemists of the previous decade worldwide, and he has also been designated a Thomson Reuters highly cited researcher. So Professor Neil Champness, thank you for accepting this invitation. It is a pleasure to have you here, and please feel free to start your lecture. We'll be listening.
Okay, thank you very much. So can you see my slides?
Yes, it is okay. We can hear you. It is very good.
Most important thing, yes, absolutely. Okay, so thank you for the introduction. Honestly, I was going to say I was very sorry that I can't be there in person. And then I watched the video and it was kind of even worse that I'm not there in person. Yeah, unbelievable. Looks like a lovely part of the world, and well, when we can travel, I will travel again.
We hope. Yes.
So recently, actually, I've recently moved to the University of Birmingham, as you can see from here. This is the first talk I've ever given from the University of Birmingham, which is interesting, and I now hold what's called the Norman Howarth Chair, which is named after Norman Howarth, who people will know for Howarth projections of sugar molecules and that kind of thing. And he won the Nobel Prize a long, long time ago. I can't even remember when. Whilst he was at the University of Birmingham, and interestingly also at Birmingham, Fraser Studdard, who many of you will have heard of, who won the Nobel Prize in 2016. He used to be at the University of Birmingham as well, and he started his work towards the Nobel Prize when he was employed at the University of Birmingham. So it's an interesting move for me. Moving departments in the pandemic was a choice, which, well, there we go. I won't do that again. But really kind of interesting. So it's a real pleasure to be able to talk to you about some of the work that we do in our research group, previously in Nottingham and now in Birmingham. So the research in my group is divided into three major areas. So we do work on metal organic frameworks and aspects of crystal engineering. We do work on interlock structures, and this includes frataxanes and catenanes. And this is very much similar to the work that Studdard did, which he won his Nobel Prize for. And we also do work on the self-assembly of molecules on surfaces. And these systems, they can look extremely different to one another. So MOFs are inorganic chemistry. I'm trained as a coordination chemist, actually. I did my PhD on ruthenium and osmium phosphine complexes and that kind of thing. So this is inorganic chemistry. The interlock structures are very much organic chemistry. And this work on surface self-assembly is much more physical chemistry or even physics. And we collaborate with physicists widely on aspects of that. So if you asked a member of my group what sort of chemist are they would give you different answers depending on which person you asked. And it can look very different and like we're just doing lots of different things. Even to members of the group, it can look like that. So what are we trying to achieve? Well, underpinning all of these different areas of chemistry is a very simple question. And that simple question is, how do you organize molecules with respect to one another? And we do that in the solid state, using metal organic frameworks, and using other crystal engineering approaches, including hydrogen bonding. We do that in solution by using interlock structures to actually position different species next to each other. So for example, these two aromatic dye molecules are placed in close proximity by the interlock structure. And on surfaces, we position molecules in 2 dimensions across the surface. And actually we use supramolecular chemistry to achieve that using hydrogen bonds. So today I'm going to talk about 2 aspects of this. It's very difficult to talk about 3 aspects of this research. So I'm going to talk a little bit about metal organic frameworks, and then I'm going to talk about surface self-assembly as we go through. So we've worked on metal organic frameworks for a long time. And in fact, we've worked on them since before they were called metal organic frameworks. So these are just some examples of the work that we've done over the years, which show you that we can try to understand the synthesis and the synthetic strategies to making these types of framework structures. So one of the very first examples we ever produced was this structure, which is shown up here, which is a very simple system actually. So this is just made from tetrahedral metal ions, so copper 1 in this case, and a simple bipyridal linker. And it makes a structure which is very similar to that of diamond. And because the spaces between the nodes of that structure, the metal ions in that structure, are so large, we actually observe what's called interpenetration, but could also be called polycatenation. So there are actually catenates formed throughout the entire framework. And this actually provides a link to the subsequent work on the work we do on interlock structures. So we can do that kind of thing. We can make chiral structures from achiral components. This structure is an extraordinary type of framework, which are actually still very rare. This is what's called a self-entangled structure. This framework actually ties knots in itself, so it weaves around itself throughout the crystal, despite being a single continuous framework. This structure down here, this is using lanthanides, and this has the same overall kind of topology as cesium chloride. And then we do some work on gas absorption studies. So for example, this framework that you can see here, once upon a time was the world record holder for hydrogen absorption in metal organic frameworks. And we held that record for a matter of weeks before we were superseded by somebody else. And that's just the nature of working in MOFs. It's a very competitive field. And there are huge numbers of groups around the world who try to study these systems. And there are now well over 100,000 MOFs known for which the crystal structure is known, let alone MOFs where the crystal structure isn't known. And it's just an enormous field now. So we study these kinds of systems and have done for a long time. Now, today I want to talk to you about something slightly different. So I want to talk to you about how you can use the crystalline framework structure of a MOF to study reaction processes in the solid state using single crystal X-ray diffraction. So this is really quite new idea, but actually comes from a very simple starting place. So for example, if you can imagine a framework structure, such as that shown here, and it has guest molecules sitting in the pores of the framework. So that's represented by these purple balls. We can then exchange those purple balls for a different species, so a green ball, and the green ball becomes ordered throughout the framework. And we can now determine the crystal structure of those those new species, the green balls, because they are ordered in a crystalline arrangement. Now, this is the basis of Fujita's crystalline sponge approach. And you can actually do this type of chemistry to try to understand the structure of extremely complex molecules, including natural products and that kind of thing. So we're more interested in, can you use this type of idea to actually study metal complexes within such frameworks, and actually look at reactions and indeed photochemical processes at those metal complexes, which are supported by the framework. So there are two different strategies to making such systems. One is that you have a metal complex which can also act as a ligand, and you use it as a ligand to make a framework. And I'll give you an example of that in a moment. This then orders the metal complex in 3 dimensions in your crystal, and you can look at different processes at that metal complex. The other strategy is what's called post-metallation, and here you make a framework structure which has vacant binding sites on the framework. And then you can introduce a metal complex after you form the framework in a post-metallation strategy, and the metal complex becomes bound to the vacant binding sites, becomes ordered, and then you can study the reaction processes by crystallography. So we first ventured into this area just about 10 years ago now. And we were interested in this species up here. So this is rhenium bipi-tricarbonyl chloride. Okay, so this system here, these are very well studied photochemically active molecules. They can be used for intercalation into DNA, and you can study how they bind to DNA. You can even make photovoltaic devices using these rhenium complexes. They're incredibly expensive, but you can do that if you so desire. And this is a compound where the photochemistry is very well understood. So all we're doing here is we're going to make this into a dicarboxylate. So we stick these carboxylic acid groups, these carboxylate groups, on either end of our bipi molecule, and we now have a simple dicarboxylate which we can use to make MOFs. So we take this and we react it with manganese 2+. You can use other metals, but this is just where we started. The manganese binds to the carboxylate. You make manganese carboxylate chains that you can see here. And then off the side of the chains are the bipi ligands, which are binding the rhenium complex. So we have these manganese carboxylate chains. Here you can see the manganese carboxylate chains being bridged through the rhenium complexes that you can see here. And then if you look from this direction, then here are our manganese carboxylate chains once again. And here are our rhenium complexes, which are now attached to the struts of a framework. So they're actually built into the framework, sitting on the framework structure. So at this point, I'm just going to point out that this particular structure, this looks porous. It isn't, okay? It's important to know that this isn't a porous structure. It's just because of the way the picture looks. It's not significant, okay? So we now have our rhenium complex supported by MOF. So we then look at the photochemistry, and we do this in collaboration with one of my now ex-colleagues at Nottingham, a guy called Mike George. And Mike is an expert in time-resolved spectroscopy. So what happens here is you shine a light on your compounds, in this case a MOF with a rhenium complex inside, and you excite the rhenium complex and it generates an excited state. So you can then follow what happens by infrared spectroscopy of the carbonyl region that you can see here, and essentially time-resolved spectroscopy. What you're seeing is peaks disappearing and peaks growing. That's what you're seeing, and you can follow this as a function of time, and this tells you whether you're seeing an excited state or not. So what happens here is that this spectrum up here, what it tells you is that you populate a metal to ligand charge transfer state and a pi star state very rapidly. But then over a 20 picosecond timescale, so incredibly quickly, you populate just the pi star state. Now, and this is what happens at 275 Kelvin, so room temperature in the UK, right? So it's this is what happens. So is this significant? Well, what is significant about this is that if you study these types of compounds in solution, the favored excited state is the metal to ligand charge transfer. So the MLCT state is what you see in solution. In the solid state or in the MOF, you see the pi star state. So you've actually inverted the energy levels of the excited state by putting this inside a framework structure. And that gives us hope that we can actually manipulate photochemical processes within frameworks like this. Now, if you study this same photoexcitation process at lower temperatures, so 200 Kelvin, you can actually see CO bands growing in. So this is actually free CO. And this then recombines with the rhenium complex because it can't escape from the framework because the framework is not porous. And it recombines, and this can result in isomerization of the rhenium center from the FAC isomer to the Mer isomer, depending on where the CO recombines. And in the case of this rhenium complex, this happens in approximately 10% of the rhenium centers. So we get 10% isomerization. And actually, 10% isn't very much. It could just be consistent with the first few layers of the surface of the crystal, in fact. It's quite possible that's about 10% of your crystal. And it's not enough for us to study this by single crystal X-ray diffraction. So we move to a related system. So we can make this analogous manganese complex here. So we now have a manganese tricarbonyl chloride BIP complex. The manganese complex is known to have higher quantum yields. And it should have a quantum yield of approximately 30%. And that would be enough for us to actually follow this process by single crystal X-ray diffraction. And we can certainly follow it by infrared spectroscopy. And in fact, this works. So approximately 30% of the manganese centers isomerize from the FAC to the Mer isomer. And we can even do this on a single crystal. We do this at the diamond light source, the synchrotron, because it gives us better data. And we can isomerize from the FAC isomer to the Mer isomer. Now you can actually see that this just corresponds to this chloride moving from this axial site to this equatorial site, like so. And you can follow that and you can model the chloride in this position, and it is 30% of the structure has isomerized. And this was interesting back in the day because you could actually follow a simple isomerization process, photochemically induced, but a simple isomerization process by single crystal X-ray diffraction using this type of approach. So we've done that work back in 2010, approximately. And then I was contacted by these guys. So this is Chris Sumby, and this is Christian Doonan over here. And they work at the University of Adelaide. They're both fantastic chemists, I mean, really brilliant chemists, and they have essentially a joint group. They do a lot of work together. And they invited me out to Adelaide and to discuss some work that they've been doing. And right at that time, they just were in the process of publishing this paper. And this paper's really fascinating piece of work. And as you will see, we've gone on to develop some of the chemistry first described in this paper. And what they did was they took this ligand here, which you can see is a dicarboxylate that has this vacant, this bis-pyrazole site in the middle. And you can react this with manganese too, just as we've done. And it makes a MOF structure. So the MOF structure is very complicated, actually. But the important thing is it has these pores, and adjacent to the pores is a vacant binding site. So you can see this here. This is the bis-pyrazole site, and it's sitting adjacent to a pore. And what they showed was that you could take these MOF crystals and you can metallate those vacant binding sites. And so this is a simple example where you just take the crystal of the MOF and you suspend it in a solution of your metal complex, in this case cobalt chloride. The cobalt chloride diffuses into the framework and binds the vacant binding site. And actually you can do this with, this paper has rhodium complexes in it as well, and you can do it with a whole variety of different metals. So this is a really kind of an interesting discovery, and we started to work with them, it's not the most obvious thing in the world to collaborate between, you know, the UK and Australia, although it is great because, you know, we get to go out to Australia and they come out to Britain. So it is possible to do this collaboration, and we have, you know, online meetings, and we've been having them for the last, I don't know, 6-7 years. And although the time difference is a bit of a challenge, it has to be said. So we started collaborating with them, and of course we thought, well, can we look at our photochemical processes? Can we look at our complexes, which we'd already looked at in our BIPI compounds? So here we take their MOF, so this is the Adelaide MOF, I'll call it, and you can react it with manganese pentacarbonyl bromide, and the manganese pentacarbonyl bromide diffuses into the framework and reacts with a bispyrazole site. And you can see over here, this is kind of a model complex. This is the molecular species of what you normally anticipate. And in the MOF, you see something slightly different. So what you see in the MOF is that you actually end up with a water ligand bound to the manganese center and the bromide sitting as a counteranion. Okay, and this is just because you, in our process, we have a little bit of water around in the ethanolic solution of the manganese pentacarbonyl bromide. And it turns out the solvent's important in this process. So here you can see this. Here's our the compound I just described. We have a bound water and a bromide counterion within the framework. If we use a coordinating solvent such as benzonitrile or indeed acetonitrile, then that nitrile group binds to the manganese. We still have a bromide counterion. If you use a relatively non-coordinating solvent, so THF or probably beta-toluene, you end up with a bromide coordinated to the manganese center. And in fact, you can interconvert between these different states by soaking your MOF crystal in different solvents. Now here are the crystal structures of all the different variations on the theme that I just showed you. Here's the coordinated benzonitrile, bromide counterion. Here's the water complex. Here's the and here's the where the bromide is actually bound to the manganese center. And we're just changing that partly as a factor of polarity, but also as a factor of the coordinating ability of the various solvents. You can follow this by infrared spectroscopy, of course, because you have a carbonyl, metal carbonyl species, and you're just changing the coordination environment, and you can actually follow this process quite easily by looking at the carbonyl bands and the different symmetries which you generate by this isomerization process. So we have this manganese center bound within our MOF. So we started to wonder, can you actually do reactions at that manganese center? And the answer is quite clearly yes. So the first thing we do is we're going to take our manganese tricarbonyl with a water and a bromide counterion, and we're going to diffuse in sodium azide. Now the azide is a good ligand. The azide binds to the manganese center. Here you can see the azide bound to the manganese center, and you can see this on all of the azides in the single crystal structure of this compound. So every single one, essentially, has an azide bound to the manganese center. Here's a kind of close-up of this. You can see the similarities to the previous structures that we've looked at. So we now have an azide, a metal azide within the framework. And what do you do with azides? Well, any organic chemist will tell you, you do a click reaction. Okay, so this formally isn't a click reaction. This is a cycloaddition reaction, apparently. So the referees correct corrected us on this. We originally wrote click reaction in our paper, and they said it's not a click reaction. Okay, if you say so. So we diffuse in an alkyne. So an activating alkyne works better. It diffuses in, and you can see from this crystal structure that the alkyne is reacting with the azide. I'll show you a better picture in a second. And it's making this triazole, and this is akin to click reactions that you see in the literature. So here you can see it from the other side. This is actually looking at the electron density. This is actually how you actually tell from a crystal structure what's going on. Here you can see the triazole species bound to the manganese center, and this is determined crystallographically. So we can actually see the different steps in a reaction sequence, and in fact we can even liberate the triazole by alkylating it with methyl bromide and generating the bromide complex again. I'll come back to that in a second. So you can do this with different alkynes. These are all activating alkynes. So you can see here, you're actually seeing the crystal structures of the products of these reactions. And if you take a dialkyne, you can actually react to one end and not the other. Okay, so we can actually now desymmetrize a dialkyne using this approach. And this happens because of the MOF structure. So if we take a dialkynes of different lengths, then we can actually look at this process. So in the crystal structure, the azides are separated by 13 angstroms. So if you take a dialkyne which is shorter than that, so this one is 10.7 angstroms, then it only reacts at one end. And we desymmetrize the dialkyne and we make a triazole alkyne species. If you take a dialkyne which is significantly longer than the azide separation, then you actually make the ditriazole compounds like this, and with still have a trace of this because we get an incomplete reaction. And if you have something which is almost exactly the right length, then you end up with a bit of a mixture of the different things. So this actually gives you some specificity in controlling that reaction process within the framework. So overall, what you're doing here is we're starting with our MOF-supported manganese complex. We react it with an azide, we react it with an alkyne, and then we can liberate the subsequent triazole species by reacting with methyl bromide, which goes back to our original species. And in principle, you can go round this cycle. So we went round it 2 times. You could go longer. There's some degradation over a period of time, but basically you can do this. And each of the steps in this reaction cycle are characterized by single crystal X-ray diffraction. So we know exactly what the product is at each individual step of the reaction. And that's kind of fun, and suggests that we can start to do this for other types of reactions as well, and study reaction processes within the framework, determining the single crystal structure of each of the steps as we go through. And there's no real reason why it has to be a metal complex. You could do this with organic reactions as well. It's absolutely the same. Crystallography might be harder, but basically it should work. So if you're interested in that kind of thing, we actually, during the lockdown, as with everyone else, we published a review. This review came out last year on this type of process and the kind of state of the art in looking at reactions inside MOFs. And all that work, which I've described, was done in collaboration with our friends in Adelaide, and we continue to collaborate with them. So that's the first part about MOFs. And now I'm going to move on to surface self-assembly. So despite being trained as an inorganic chemist, as I was, I always had a sneaking admiration for organic chemistry. And I have to admit to that actually some organic chemistry is really quite cool. And I was always interested by this work, which was summarized by George Whitesides a long, long time ago, so back in '95. And in this review article, he summarizes the work that he'd done, and it was also developed by Dick Reinhout in the Netherlands, and also Mark Maskell, who happened to be in Nottingham as well at one stage. And what you're looking at here are different things that you can do with hydrogen bonded systems. So essentially, this is taking a molecule which is called melamine. So the ones with the darker grey in here, this is called melamine. And melamine, when you polymerize it, is used to make the surfaces of kitchen sort of tables and that kind of stuff. You'll come across melamine regularly. And this will hydrogen bond through a triple hydrogen bond that you can see here to what's called cyanuric acid. And if you combine these two, they actually make two-dimensional sheets, as you can kind of see here. If you play with the chemistry of these systems, you can make more complex systems. So you can make tapes, you can make rosettes. So for example, if you take cyanuric acid and you replace one of these nitrogens with a carbon, those are barbituric acids, and barbiturates are enormously well-studied systems. There's vast chemistry, and you can actually use that type of chemistry to make very intricate structures using this approach, and it's very cool. I mean, they're really nice systems. So we were interested in these types of using these strong hydrogen bonds. These are triple hydrogen bonds. We're interested, could you use these to organize molecules in the solid state? And essentially as mimics of the bonds that you use in making metal organic frameworks. And ultimately, we did actually do that and even make porous systems. And this is now a field in its own right, which is called, they're called HOFs, which are hydrogen bonded organic frameworks, which I personally think is a terrible acronym, but anyway, anything which sounds like MOF apparently is good for the literature. So we were interested in these things, and we started studying them in the solid state. But it occurred to us, could you actually use these types of interactions to organize molecules on surfaces? This is a two-dimensional structure, as shown on the screen here. Could you do this on a surface? So we started to look at these systems. So this is a simple diimide. Okay, so this naphthalene diimide in this case, this has this same imide unit on the end, which is basically the same as one face of cyanuric acid, and is also extremely related to DNA nucleobases, as we'll come back to in a bit. So this hydrogen bonds to itself in the solid state. This is the crystal structure of this compound, and it forms this double hydrogen bond, as you can see here. Okay, so we then collaborate with some physicists, and in particular with Peter Beaton, who still is a professor in Nottingham, and they're very good at scanning tunneling microscopy, so STM. So if you deposit these onto a suitable surface, this is actually silver terminated silicon, you need a surface where the molecule will absorb but is free to move around, and you need that motion for self-assembly to take place. So if you look at the anhydride, where you don't expect any hydrogen bonds, you just get molecules moving all over the place, and it's very kind of diffuse images, and there's no regular structure. If you look at the imide, you can see straight away that there is regular structure across the surface. And if you look in more detail, this is what you see. So each of these white features, each of these things here, is a single molecule. And those single molecules are arranging themselves into these linear chains. You can measure the distances between the single molecules, and this corresponds almost exactly to what you see in the crystal structure. And you're seeing the assembly of chains through hydrogen bonds in one dimension. Now, you might think that you can see a difference as you go along the chain. So you might think this is a bright feature, this is a darker feature, this is a bright feature, this is a darker feature. So that's actually correct, right? That's not your eyes playing tricks on you. That's because the molecules are sitting on different surface sites, and the energy of the orbitals is actually slightly different. And you can pick that out using STM. It's, you know, an amazing technique. So we can see that, and this was kind of interesting to us because it was just the same as the crystal structure. We thought, well, okay, well, we can use our knowledge from crystal engineering to design structures on surfaces. So this is a one-dimensional system. Surfaces are all about two-dimensional systems. So we learned from the Whiteside's chemistry, and we take this slightly longer molecule, which is for geometric purposes, and melamine. And melamine should form a triple hydrogen bond to the ends, these imide ends of this molecule. So you should form this triple hydrogen bond. Each melamine should have 3 of the imides sitting around it. Then the melamine should sit at the other end, and you should make a honeycomb structure. So this is what you see. These are the STM images. We can grow them over whole surfaces. Over here, you can see each of these white features is the perylene diamides, that long diamide molecule. And you can see 3 of them coming together at a vertex, which is where the melamine sits. The thing which is amazing about this, to me as a chemist, is you can see everything which goes wrong during the self-assembly process. So, for example, there is a missing molecule here. There should be a molecule there, and it's not there, right? There should be a molecule here, and it's not there. And you can see all these defects because you're actually working at the molecular level. And this is completely different to almost any other technique that chemists use. So crystal diffraction is an averaging technique. NMR, you're looking at billions and billions of molecules at a time. Here, you're looking at individual molecules, and you see everything which goes wrong. So in some sense, this is a porous framework, right? There are big holes within here where we have exposed surface underneath. These pores are 2.5 nanometers across, and they are suitable for absorbing C60. We can actually absorb lots of other molecules as well, but C60 was a good starting point. And the C60s essentially roll across the surface and are trapped within these pores. So this is a 3-dimensional representation of this image. The image on the right is a representation of the image on the left. And the hydrogen bonded array is essentially like an egg box, right? And there's C60 molecules are sitting within the pores. And if you look in more detail, you can actually see that there are 7 C60s all sitting in the pore at the same time. So there's 1 in the middle here, and then 6 around the outside. And those heptamers form because it's the right size and shape. There's nothing more clever than that. It's just the right size and shape. So this is where we started in this field. So all the work on the perylene diamide systems and naphthalene diamide systems is all covered in this review, apart from the stuff we published afterwards, but basically a large proportion is published in this review. And I'm not going to go into any more detail about all of that, but needless to say, we worked on that or have worked on that for a long period of time. Now, I want to talk to you about something slightly different. So, of course, while we're doing this surface assembly, we are also working on MOFs. And we've been working on this series of compounds where we take copper-2 and we react with these tetracarboxylic acids, right? And these form a nice series of MOFs, and they happen to be good at hydrogen storage again. And again, this one in the middle here, this again was a world record holder for a short period of time. And I think what I'm showing you in this slide is twofold. The first one is telling you that we had a whole series of carboxylic acids available to us anyway from other chemistry we were doing. And the other thing is that we can actually change the structure of these really quite simply. You can make them longer and longer and longer as you see fit. And then you can start to look at the surface self-assembly of those systems is what we thought, you know, carboxylic acids, hydrogen bonds, so why not? So we started with this system here. This is a 4 phenals tetracarboxylic acid. We can deposit this onto a surface, in this case graphite, And this is actually imaged under the solution, so under nonanoic acid, which is just an STM solvent. It has the right conductivity properties for STM. And you form carboxylic acid dimers, as you can see here. Each of these features is an individual molecule. So you can see that. We then thought there was a paper back in the 80s in Helvetica Chimica Acta who said that coronine is the right size to fit within 6 isophthalic acid units like this. Okay, so we thought, can we add coronine? The answer is yes. Here's coronine added to the same solution, the same drop of nonanoic acid. The coronine absorbs to the surface strongly because it's interacting with graphite, and you end up with 6 of these molecules, these tetracarboxylic acid molecules surrounding each of the coronines. And we thought, well, okay, so this is kind of cool. Let's change the length of this molecule. So we've got all these systems. We can just look at this and just make a systematic study. So we move from this tetraphenyl system here to the terphenyl system that you can see up here. Okay, so this should, in principle, do the same thing. This is the STM image that was recorded. So I want to people to just look at this just for a moment. Each of the bright features is an individual molecule. And if you pick any molecule you like, I don't care which one, and go in any direction you like, and just go from, say, this molecule to this molecule to this molecule to this molecule to this molecule, just move in a straight line, and you'll see that there is no translational symmetry. So this doesn't actually form a regular structure. This forms this really quite bizarre system which has no translational symmetry. And we, as chemists, we're not used to that. We're trained from day one to look for symmetry from the structure of sodium chloride, right? So we're told sodium chloride has this regular structure, and we look for symmetry in everything from that point on. This system has no symmetry. It doesn't have rotational symmetry either, but it certainly doesn't have any rotational as translational symmetry. So why does this happen? Well, the first thing to note is the distance along the molecule, shown as D2 here, is the same as more or less as the distance across the carboxylic acid hydrogen bond. And this means that if we think about how these can arrange, let's just remember back to the system, the previous system, where we had a coronine molecule surrounded by 6 isophthalic acids. So we can form that same pore by 6 molecules, by 5 molecules, by 4 molecules, by different 4 molecule arrangements, or indeed by 3 molecules. And because of this geometric relationship between this distance and this distance. And you pick these out in the STM image. Here's the 3 molecule system, here's the 4, here's the other 4, here's the 5, and here's the 6. So they're all there, they're all there. And it was at this point that we realized we were being stupid. And actually these molecules are rhombuses, right? So you can actually now understand what's going on. So the ancient Greeks knew that rhombuses tile 2-dimensional space in a random fashion, right? This was known, it just wasn't known to people of my age in the UK. So once you realize this, then we can start to think of this as a rhombus tiling. So we're just going to color our molecules in. We're going to, something horizontal is red, something up to the right is green, something up to the left is blue. You take your STM image and you color each of these in. And eventually you end up with an image which looks like this, right? And the thing which is really interesting about this, in my opinion, is that every time you do this experiment, you will get a different structure, right? Every single time you get a different structure. There are essentially an infinite number of variations on the theme. So that's kind of interesting. So as a supramolecular chemist, we spend our lives trying to make things predictable and saying we know how to make whatever by assembling these molecules. I can guarantee that I don't know what the product of this will be. Absolutely guarantee it. And that's really unusual. for any type of system actually. So you can study what affects how random the structure is. So it's affected by the solvents to some extent, by temperature. You can have a guess to actually get rid of the random nature, such as coronene. And these are lovely systems to work on. So it turns out that these are related to something called Penrose tiles. If you don't know what Penrose tiles are, the Wikipedia page is fantastic. Go read the Wikipedia page. And these are systems, they have no translational symmetry, but do have rotational symmetry. So Penrose tiles have rotational symmetry, and they're actually mathematical models related to what were then discovered as quasicrystals. So this is one of the most famous Penrose tiles, which this has fivefold symmetry because of these little pentagons in here. But there is a Penrose tile which is based on rhombuses. Actually, the Penrose tile is based on fat rhombuses and thin rhombuses. Again, you can actually see fivefold symmetry in here, but nonetheless, this is based on rhombuses. This is the floor of the chemistry department in the University of Western Australia in Perth. They built a new building and they built a Penrose tile for their entrance hall. It's quite an amazing place to go. And they actually explain how they convinced the builders to work, to build the Penrose tile, because it wasn't an easy thing to do. This is actually the maths department in Oxford. So Penrose is a mathematician and he is an emeritus professor at the University of Oxford, and they have a new maths building, and outside the maths building, this is the floor, and it's a Penrose tile. And you can see here, it's close up, and you can see again the fat tiles and the thin tiles. So we became interested in tiling processes. And this led us to this person here. This is another mathematician. As you can tell, this is a relatively old mathematician. And this guy is called Major Percy McMahon. He was a soldier in the British Army. He served in India in the 1900s. And when he left the army, he became a mathematician at St. John's College in Cambridge. He published this book. You can buy this on Amazon, this book. And I have a copy in my office, not behind me. And this is kind of interesting. So it sets mathematical puzzles for people around tiling processes. And these used to be published in the Times of London in the 1920s. And people apparently were clever enough to solve the mathematical problems, which I guarantee they aren't now, except for the occasional mathematician. So they're really interesting. And the basic thing is, so this is an example of one of his tilings. Here we have, 24 different tiles, right? So each of these tiles is different. And he's numbered them on each side with a number. And where they meet a tile with the same number, they can actually stick to each other and they form an arrangement. And it is possible in this case to have 24 different tiles will form a discrete assembly of 6 by 4, like so, okay? And the whole of this book is how you work this out, right? So I looked at this as a chemist and I thought, so what if you could actually make 24 different square-shaped tiles? Could you then arrange them so that they make a discrete species? And this would be so far beyond what we can do as supramolecular chemists, it's unreal, right? So the world records for the number of different components is about 6 at the moment. This would be 24 if you could do this. Hugely challenging, right? Hugely challenging, but we thought, let's have a look at this. So I see a square tile and I think of porphyrins. It turns out that this is a mistake. Porphyrin chemistry is terrible in my experience. So I wouldn't encourage anyone to do porphyrin chemistry particularly. But this was our starting point. And we thought, let's take a porphyrin and we'll stick different hydrogen bonding groups on either side, right? So we thought, let's go with DNA nucleobases. Why not? We'll try to put different ones on each side and we'll see where we get to. So it turns out this is quite hard. But nonetheless, we've made some progress. So here's the tetrathymine compound you can see here. This turns out to be really insoluble. So for solution studies, we made the model compound with just one thymine coming off. And we also can make small adenine model compounds. This is the crystal structure of the model complex, and you can see thymine-thymine hydrogen bonding as you would expect. And I'll remind you that this is very similar to the naphthalene diamides that I showed you earlier. It's the same hydrogen bonding structure. So we can deposit this on surfaces. This is done in collaboration with Matt Blunt, who now has his own group in UCL in London, and was actually the postdoc who did the rhombus tilings when he was a postdoctoral researcher. So this is the STM of the tetrathymine molecule, and it hydrogen bonds through thymine-thymine interactions. Okay, which is great. You can add the model adenine compound, and it forms a bit of a mess, to be honest, but there are regions where you're seeing this arrangement. So this has both Watson-Crick hydrogen bonds, but also other hydrogen bonding arrangements in here. And this is not a simple process at all. So we then thought, okay, so if we've got the tetrathymine system, can we make the tetraadenine system? Again, we can make a model complex, and this forms adenine-adenine interactions. These are actually Hoogsteen hydrogen bonds. And we're going to put a zinc in the tetrathymine molecules so that the STM looks different, right? You're just slightly changing the energy levels for the STM. And we can deposit the two on a surface, and this is what you see. Now, if you look carefully at the STM image, you have the bright features, which is where the zinc atom is, and then slightly lighter features, and then brighter features, then lighter features. And this is forming an alternating structure, in fact. So what is it doing? Well, this is the structure that it forms. This isn't what we were anticipating. We thought we would just adopt simple Watson-Crick hydrogen bonds, but actually it forms this quartet structure. So those of you who are more biologically oriented or more biochemically oriented will know that quartets are actually not uncommon in DNA structures, and particularly guanine quartets, which are of importance for cancer. So you do see Watson-Crick hydrogen bonding, but you also see these other interactions, and you end up with these quartets of alternating adenines and thymines. And it kind of works in terms of forming a tiling arrangement, but only but in a way we didn't anticipate. And that's because the chemistry is much more complicated than you imagine. So now, I've just told you what the structure is from this particular image. Now, you're taking on, there's a lot of trust in there. I'm telling you that this is the hydrogen bonding arrangement from this image. There's obviously a lot of modeling which has gone into it, but you can't see the fine detail. So that wasn't possible until this paper came out. This is work by Leo Gross at IBM in Zurich, who developed a different scanning probe technique called non-contact AFM. And non-contact AFM is like AFM, except you have a CO molecule on the end of the tip, or a molecule on the end of the tip, and you image with that molecule, so the oxygen of the CO in this case. And you can get submolecular resolution. So here's the submolecular resolution. And you can see individual bonds in a molecule. And that's pretty amazing, right? So this is pentacene. This is a carbon-carbon bond. This is a carbon-hydrogen bond. So I went to one of my colleagues and said, so could we do this and try to look at hydrogen bonds and get submolecular resolution of a hydrogen bonded array? So the system we chose was this one. It's going back for us to this naphthalene diamide system. There are double hydrogen bonds in here. And this image doesn't show you the hydrogen bonds. We can just measure distances. So we work with this guy here. This is Philip Moriarty, who's a fantastic scientist. And the postdoc who actually did this is a guy called Adam Sweetman, who we now collaborate with on different aspects of this. And what happens here is that you pick up a naphthalene diamide molecule on the end of the tip. And if you do it right, this carbonyl is pointing downwards, and it's a bit like a CO. And you can image with that carbonyl oxygen atom. This is the scanning tunneling microscope image. This is a normal atomic force microscope image, and this is the non-contact AFM image. And if you look in more detail, this is what you see. So you get submolecular resolution. And in fact, you can even see lines where there should be hydrogen bonds, right? Now, this paper actually goes into excruciating detail about why these are not the hydrogen bonds, right? These are actually, these lines arise for other reasons, but nonetheless, they are where you expect the hydrogen bonds to be. And we get a submolecular resolution image of a hydrogen bonded array. So this gives us hope for studying much more complex systems by scanning probe microscopy, in particular non-contact AFM, where we should be able to describe exactly what is the interaction between different molecules. And this is obviously something which we pursue at the moment on our different tiling arrangements. So this stuff, so the state of the art in non-contact AFM is reviewed in this article, which was written with Adam Sweetman, and also a guy called Alex Saywell, who's an STM guy who we also collaborate with. And this came out last year as well. So that is all I'm going to talk to you about today. I need to thank a whole raft of people. These are the people who are currently members of my group. And then there's a whole bunch of people who have been members of my group over a long period of time. I'm particularly grateful to the physicists I collaborate with. So particularly Peter Beaton, and also Philip Moriarty and Adam Sweetman, and then Matt Blunt, who's at UCL, Mike George, who does the spectroscopy on the work I've talked about today, and then my collaborators in Adelaide, Chris Sumby and Christian Doonan, and particularly Michael Huxley, who's just finished his PhD, and also Rosemary Young, who did a dual PhD between Nottingham and Adelaide. And got stuck by the pandemic, which was pretty horrendous for her. And then we work with lots and lots of crystallographers over the years, as you can see here, and particularly Diamond Light Source. These people have given us money for lots of different things over the years. And finally, thank you for the opportunity to come talk to you this morning. I wish I could be there in person, and hopefully I will be able to in the future. And I'll leave it with that. Thank you very much.
Thank you very much, Professor Neil. It was a great lecture, and we have time for a few questions, a minute. I don't see here any questions. So can I just, it's just curiosity, and can I just ask you, the interest from the industry, as far as understood, there are probably many interests for energy applications, and probably yes, or if they are already in the industry commercialized or not, the several strategies that you present. But can I ask you about the food chemistry? Is there any interest on the industry of food, of the food industry applications of
food?
Some of these strategies, or is this scalable? The cost is it cheap, or what do you think? Can you comment on that?
Okay, so MOFs have started to be used in agriculture in different ways, actually, in particular. And I think, so there are studies, they're quite good for, they have been developed for drug delivery. So they can release molecules. They, particularly the ion systems, and the ion systems have become more and more topical for biological applications, and include food in that, right? So there is interest in that, and some people, I believe, have started to commercialize that. Yeah, there is that. That's kind of an interesting area. There is also interest. It's probably not as relevant to our two countries, but a really growing area is actually water capture. So taking water actually from the air. So there are moths which have been reported which can actually take water from the air in a desert. So I mean, they're really quite amazing. And obviously this is really important in the Middle East, for example. I mean, obviously, but also in parts of America where they have water droughts, right? So that's a really important kind of development recently, and I suspect, well, I have no doubt that will have importance for agriculture, actually, no doubt whatsoever, and it's really important. In terms of scaling up, it depends on the particular system you're looking at, but some moths you can make on whatever scale you like, right? So ton scale, potentially. So there are various ways of doing that, and there are various companies who do that. There's one in the UK called Moth Technologies, who use a mechanical process for making the moths, and that works. BASF make moths commercially. So it's starting to really develop to the wider world, and it's totally possible to use these systems for commercial applications, as long as your ligand isn't too complicated. Let's just make that clear. If your ligand's complicated, it's a different thing. But yeah, so really developing.
Okay, I just see here some question. I'm trying to read. Nice talk, Neil. I'm just reading a question around the reactive complex in moths. Do you see this as more of a tool to study chemical process mechanisms in the solid state, or do you think the idea might actually involve as practical method for catalysis? I don't know if you understand.
Yeah, I do understand. Yeah. So, okay. So we study them more for understanding reaction mechanisms, but there are a lot of people who study moths for catalysis. Usually with different types of reactions to us, or different types of systems to us. We actually are now trying to study these systems as reaction vessels, basically, right? I guess the limitations are scale up there, right? And that is a question, although there are approaches to that. So for example, you can make something called monoliths, so moth monoliths, which are just basically big chunks of moth, right? So, literally that big. And you can, in principle, you can actually do reactions by reacting things through the moth. And that's something that we're developing at the moment. So it's a mixture of the two, right? I think the more immediate thing is understanding reaction processes, but there is definitely hope for using them as, for reactions. Okay.
Okay. Well, let me look at the time. I think we are finished. I just wonder when another comment. Is there any safety issues to look at when you, for instance, when you apply in agriculture or when you try to apply in health systems?
Yes is the answer. And I think although there are quite a number of studies of that, so what happens when someone eats a moth or injects a moth or whatever. So obviously some metals are not good for you, clearly, but you can avoid those, which is why a lot of people have looked at iron, because iron's okay. The ligands does become important. So it turns out that actually a lot of the simple ligands are fine, right? They're not a problem at all, and are processed by the body in a really simple way. Some obviously aren't. There's some wonderful work by Fraser Studard's group on what are called edible moths. So they they use cyclodextrins as ligands, and cyclodextrins are just sugar, right? So you can do that. It is possible to have completely safe systems, and that is an area which is being developed. But of course, you need to be careful, right?
Okay. So
Right.
thank you again, Professor Neil, for your presence here. It was an excellent talk. So we should move to a break and for poster sections, and then we'll start again at 11:30, I think. Yes, Ines, if you can say a
Yes.
word. Thank you.
Yes, thank you. Thank you so much. Thank you, Dr. Neil, for your talk. It was wonderful. Thank you again. Congratulations for your work. Thank you, Dr. Susanna, for being chair of this session. Congratulations to you both. So as Dr. Susanna was saying, let's move on to the break and poster session. So I invited all of you to visit our Congress website and see the posters. They are divided by area. And if you want, you can start voting on your favorite 3 posters. So I'll see you at 11:30. Thank you so much. See you soon. Bye.
Tem alguém? Tu? Alguém em linha? Estão a ouvir?
O Dr. Luís Mafra,
Olá, sou eu.
Helder Gomes, tudo bem?
Tudo bem, obrigado. Dá para experimentar assim rápido? Só mesmo para ver se isto... Consegue-me ouvir bem? Só para ver se o som está a sair bem?
O som está bom.
Perfeito. Posso lançar a apresentação para ver se funciona?
Pronto, eu penso que sim, eu não sei se sou eu que tenho que dar autorização para partilhar. Deixa-me. Vou aqui tentar.
Em princípio não há problema, mas...
Sr. Helder, Dr. Luís Mafra.
Olá, tudo bem?
Eu estou a partilhar ainda estamos a partilhar o...
Ok. Era só mesmo para ver se
estamos
isto...
na sessão de pósteres. Sim.
Ok.
Está bem?
Sem problema,
Já
sem problema.
partilhamos a vossa apresentação e já partilhar a sua apresentação. Obrigada.
Eu vou ter que. Eu estou aqui com dificuldades em ver a minha janela, Lídias.
Porque eu estou a partilhar, porque nós estamos a partilhar o que está a aparecer no YouTube. Toda esta nossa conversa também está a aparecer no YouTube. Estou a partilhar um PowerPoint para as pessoas poderem votar nos pósteres. Eu já vou tirar a partilha daqui a um bocadinho, está bem? Obrigada. Hello again, everyone. Let's begin the second session of the morning. I pass the word to Professor Elder Gomes, that will be the chair of this session. Professor, your turn. Thank you.
Many thanks, Ines. Good morning to everybody. We will start now the second section of this day. The first session was the plenary lesson, very interesting one. And now we will start the session of oral communications. We have first invited lectures that will be delivered by Dr. Luis Mafra, and after we will have 3 oral communications. I will first introduce Dr. Luis Mafra, and after we can start. Dr. Luis Mafra comes from University of Aveiro. He is principal researcher at CSECO. In 2006, he obtained his PhD from the University of Cayenne in France and in the University of Aveiro, working in solid-state NMR spectroscopy. In 2011, he was postdoctoral fellow at Max Planck Institute at Mainz in Germany, and he received various honors and awards, including the European Research Council Consolidated Grant in 2020. His research is focused on the combination of solid-state NMR techniques with XRD and computational methods to study intermolecular interactions in small molecule pharmaceuticals, heterogeneous porous catalysts, and carbon dioxide sorption mechanisms in porous media material interfaces. The title of the talk of Dr. Luis Mafra is Unrevealing Carbon Dioxide Sorption Mechanisms in Porous Adsorbents via Solid-State NMR and Modeling. Luis, when you want, when you are ready, you can start.
Can you see my slides?
Not yet.
I'm already presenting.
Yes.
And now?
Maybe I can ask the help of presentation.
It's already in presentation mode in my computer.
No, we are not able to see them yet.
So what can I do? I mean, I'm pressing slideshow, and I have my full screen occupied with my PowerPoint. Any suggestion? Because I have no idea.
Bruno, you can help.
Yes, do you have 2 screens?
Yes. I have
Perhaps try to open first the PowerPoint and open as a presentation mode. And then when you put share screen on Zoom, just select the presentation, not the whole desktop.
Let's see here. Maybe I should do duplicate. Let me see. Can you see it now?
No, not yet. Actually, we are just seeing your camera. We cannot see anything else.
So guys, I'm presenting already here, so I don't know what he's going really.
So
Let me just disconnect this from the. Okay, I will try to disconnect this from my second monitor. Maybe it works. Okay. And now, do you see something?
We cannot see nothing.
No, it's still the same.
You are sharing your screen, huh?
I'm in a single computer now, in my laptop.
Yes.
Yeah, but it's like you're not sharing anything.
Sorry?
It's like you're not sharing the screen because it doesn't appear anything. It doesn't. It's just still your camera.
Yes. Wait a minute. I think is okay. I know the problem already. Sorry, guys. I think I got it. Project extend. And now, can you see now? I hope.
Yeah, now I think it is okay.
Oh my God, yeah.
Okay, thank you.
Sorry, guys. This is embarrassing, but
We start sharing, but we don't see yet the slides.
yeah.
Okay, now yes.
Zoom quit unexpectedly. Send to Zoom. What the hell?
The floor is yours. You can start when you want.
Can you see it now?
We will see it before, not now.
I don't know what's happening. It's disconnecting from Zoom. I mean.
Yeah, I think disconnect you before.
Okay, let me check again. And now?
I think now it's starting. Yeah.
Okay.
Now we got it.
Okay, let me start right away. So, good afternoon or good morning. Thanks for the introduction, Helder. It's a pleasure to be here presenting from my house. Unfortunately, we cannot see each other, touch each other, but we are getting used to that nowadays. So today I'm going to bring a very different topic. I will not go into the physics of the technique. I will go into the chemical problem, which I think it's more important. We are in a community of young chemists. So today I'm going to talk about how to unravel CO2 adsorption mechanisms using spectroscopy and computational methods. Okay. Trying to pass and nothing happened again. Okay. So as you know, global warming is a major issue. To contribute for that problem are anthropogenic emissions. So about 80% of greenhouse gases come from carbon dioxide, and emissions visualized by economic sector contribute, the sector that contribute the most for CO2 emissions are production of electricity, heat production, transportation, and so on. Most of these economic sectors, they are driven by burning coal, oil, and natural gas. As you can see here from these recent statistics, coal is still a major, the major fuel used worldwide. Okay, so if you want to be serious on mitigating global warming, we should attack the problem from the root. I mean, from large point sources like coal-fired power plants. So, and there are three technologies to achieve that, which are named here on the right side. One of the most promising ones, which is the front runner of the technologies, is called post-combustion CO2 capture. So this technology has been used for decades already by using liquid amines, scrubbers. So basically, it's a solution of amines where we dissolve CO2, and then CO2 reacts chemically with these amines. And these amines, then the solution absorbs the CO2, and then it gets regenerated again to be reused again later. But there is one problem with this technology. They require very high regeneration energy. So it's very costly, this technology. Also, it produces toxic vapors, it's not environmentally friendly as well. So to mitigate this issue, to overcome this aspect, solid solvents are promising replacers. The desired materials must comply with the 3 properties that are listed here. Let me see, pointer. Yeah, are listed here. And as you can see, technology must be compatible with several properties. So we should be able to operate at low temperature, should be moisture tolerant, and should also be compatible with the use of very low CO2 pressures. And why? If we look at this table, where we have in different columns different gas mixtures from different origins, I highlighted the column specifically from coal-fired power plants. As you can see, CO2 is very dilute, okay, and also other gases. The most abundant gas is nitrogen. So the main objective here is to try to separate CO2 from the other gases, mainly nitrogen. Okay, and for this purpose, there are many materials. We had the first speaker that discussed about MOFs, which there is a lot of people now trying to use MOFs for this purpose. Before talking about MOFs, I would like to say a few words about zeolites, which are very ubiquitous. They are used for almost any kind of chemical reaction, catalysis, gas separation, gas exchange, cation exchange, and so on. However, they are not good for this application because they are not moisture tolerant. I mean, once you expose this material to CO2 and water competitively, it will prefer to absorb water. And once water gets in the voids of zeolites, it's very difficult then to get rid of water. You need to spend a lot to heat the material to several hundreds of degrees. Okay, so in terms of energy, is not really the best strategy. Okay, so we need other materials. MOFs have been proposed for already some years, but they also suffer. They are prone from degradation. They suffer from chemical instability and other issues. This is very much because they have a metal cluster which binds organic ligands, and this is the weak point of the MOFs. Okay, these metal ligand connection can be easily hydrolyzed, or if exposed to air, also can degrade very easily. So I will not discuss about MOFs in the framework of CO2 capture, but we are left with silicas, which are very robust materials. They are made of pure silica, so they can be doped with metals as well, and they can resist up to 400, 500 degrees, and they can be easily functionalized as well. There's only one concern here, one problem. I will not, unfortunately, be able to show you the very nice MOF figures that previous speaker shown, because they are mostly amorphous, these materials. Okay, so what is the motivation to study all this? It's really to try to build an atomic level understanding of the CO2 sorption mechanisms. So if you are an engineer, you think about a process, a chemical engineering process. If you want to use a process where you use a material to capture CO2, you need to think about what are the desired solvent properties for your process. Okay, and I'll list here a few of them. Okay, here. So you need to have a material which is selective for a certain gas in a mixture, which has good cyclic stability, which has a decent absorption capacity for CO2. The absorption kinetics should be favorable as well, and should be stable, of course. If we now enter inside the core of a solvent material, which I represent here, sorry, on the right side, if you enter inside the material, so you have 3 layers, you can subdivide the material in 3 layers: an external layer, which is an organic layer, an organic layer, and then a gas phase layer. A lot have been done to study textural properties, studying pore volume, surface area of different kinds of materials. Also, a lot has been done to study surface modification, but still, as the previous speaker said, you know, there is a lot to learn from organic chemists. And I'm very much into that with my group now. I'm trying to take inspiration from organic chemistry. There is decades of experience in very interesting reaction paths where we can mix with this material, because these are hybrid materials. We have inorganic part and we have an organic portion. So we are trying to develop new strategies based on smart functionalization strategies. And the whole idea behind that is that we want to understand gas-solid interfaces. So this red part here that highlights here, because this is absolutely fundamental to understand the regenerability of the material and the cyclic stability if you want to reuse the material many, many times. In order to have a good commercial material, we need to be able to regenerate the material over thousands of cycles, which we are far from that, still far from that. Why? Mostly because we don't know what are the molecular mechanisms that leads to the degradation of these materials yet, because it's difficult to couple spectroscopic techniques, you know, under real conditions, real industrial settings, you know. It has always been a challenge to try to do spectroscopy very close to real world conditions. And that's the challenge also in this project. So, and then we have another variable, which is the gas phase. So we may start with pure CO2, and then we evolve for binary mixtures. It can be of different kinds. And then you go to ternary mixture, and finally you try to mimic the flue gas mixtures from the real exhaust from a fire coal power plant. And all these will change the type of species that are formed at the surface of these materials. This adds a considerable complexity to the problem, and we need to break this problem to smaller problems, okay? To help me on that, to help the group on that, of course, we can, so to understand, to try to narrow this knowledge gap between the microscopic world on the left side, where we want to understand the solvent properties, and the microscopic properties, we need, of course, to apply surface-enhanced NMR methods in conjugation with smart surface modification strategies, and also labeling strategies, because NMR is a very insensitive technique. So we really need to rely on also smart labeling strategies, where you can inject a spy nucleus and really follow what's happening through observation of carbon spins or oxygen spins and so on. And we can easily buy these to several providers, where we can custom made some gas mixtures where we have key gases that are labeled, and then follow the reactions and help us in elucidating different paths, reaction paths. So, and of course, 1 and 2 will help me to understand 3 here, okay? What happens at this interface where the gas interacts with the surface. So let me tell you something about the material, the target material I will talk today. So they are amine-modified porosilicas. They are basically amorphous materials, but with a well-defined pore structure. They have 5 to 15 nanometers across, and they can be decorated with amine groups varying in density, nature, size, and so on. On the right side, I give you an example where you can graft different amines with different bulkiness, different sizes. So if it's too big, of course, you have less pore volume. You may also, instead of grafting, you can just physically impregnate different polymers, okay? And it's just 2 examples. There are a plethora of different molecules you can have, you can just put inside the pores. And then there is also a zoo of a species that can form once amines that are grafted on the surface or impregnated, they react with CO2, okay? So these are already amines that have reacted with CO2. You can have single molecules, you can have pairs of molecules, you can have then the intervention of water. Water comes in and can transform in bicarbonate or carbonic acid. And you may have other types of synthents. There are probably over 20 different kinds of species that can form here. And traditionally, a lot of work has been done on infrared spectroscopy, but infrared is not transparent. I mean, the materials are not transparent to infrared. You have matrix effects, you have a huge band overlap, and all of you know how difficult it is to really try to understand species, speciation, different, I mean, functional groups which are very similar across these different entities. It's basically an impossible task. Apart from that, these species are often very dilute on the surface. So you need to have a very sensitive technique, and NMR is very insensitive by nature. Okay. Another problem is that the chemical shifts are very, the chemical shift window is very narrow as well. There is also a lot of overlap in NMR chemical shifts, in carbon specifically. So I also would like to tell you that there are various mechanisms for CO2 capture that have been proposed, taking inspiration from amine solutions. I show here two paths, two routes for these mechanisms, for some of these mechanisms. One at the left that leads to the formation of an iron pair, if you go down this way. And in given conditions, it may also yield urea molecules, urea linkages. Once urea is formed, the system doesn't go back under dry conditions, and the activation occurs. At the right side, you have a different path. So here you need only 1 mole per 1 mole of CO2, 1 mole of amine pair, 1 mole of CO2, and you form carbamate, and then with water, you can form bicarbonate molecules. Okay, so the stoichiometry is basically different. These ones doubles the stoichiometry. It means that you have a higher CO2 capacity. It's very important to understand these paths, because one-to-one stoichiometry will increase the concentration of amines inside the pores, and this is very desirable, of course. So our endeavor into this realm of CO2 capture mechanisms started in 2011. And we published a paper in Chemistry of Materials where we proposed for the first time a different reaction path, different from the one I showed you just previously. We could identify a third entity, another molecule, which is called carbamic acid here, okay, which was thought impossible to form in solid surfaces. This was identified in solutions by liquid NMR, but because of its high instability, it's hard to isolate it in solid surfaces. However, you could see a peak here, okay, at room temperature. You could see this peak labeled in blue that with just 5 minutes of vacuum is gone. So it's very unstable. And this was previously assigned to urea, okay? But urea is very stable, okay? And it doesn't go away easily with 5 minutes of vacuum. You need really to heat it a lot. Even heating, it doesn't go away. You need to put water inside, okay, to reverse the reaction. And this is all under dry conditions, okay? So we immediately thought that it was carbamic acid. And this was the first indication of existence of carbamic acid that could explain many other pathways to the formation of adsorbed species. So then we were interested about that. The impact of the nature of the amine molecules in the performance of the CO2 adsorbent was already being sought, but at the but not at the atomistic level. So most of the works are made by engineers that try to just see the properties of the sorbents in terms of adsorption capacity, selectivity with other gases, but atomistic level studies are still highly lacking, okay? So many papers like this one just show one example, and many questions to answer. What mechanisms of CO2 chemisorptions exist using different amines? What's the influence of the silica matrix in CO2 speciation? Another question could be how the nature of CO2 species change after multiple sorption in desorption cycles. Can we understand the role of other gases, contaminant gases, on realistic gas mixtures? How water influences all this, you know? Some people talk about moisture-induced CO2 species, and some people talk in the literature about that water can further enhance CO2 capture, but nobody knows the mechanism at the atomic level. So the group was very much into that. And today I will talk about these two aspects, okay? So first, we were curious about many papers saying that when you change the bulkiness of the amines, you have radically different species that are formed, and the material present very different properties. So we took the liberty to functionalize our silicas with these 4 amines that are very different in terms of chemistry. So we have a primary amine here. We have a secondary amine, then a diamine, which has a primary and secondary amine, and you have now a very bulky amine, tertiary amine, which should not chemically bond CO2. It's so hindered, chemically hindered, that it's not able to really bond CO2. And this is well known already in literature. So let's see what happens. So we graphed it on benchmark silica, SBA15. We were not worried really to use, top-notch materials. The group is not so much concerned in using the best materials available. We just want a material that works well, which has been well characterized, because we want to chase these species that nobody knows about, or very few people knows about it. So we collaborate with a colleague in Technical University of Lisbon, IST, Moisés Pinto. He's a professor there. And I've been collaborating with him for several years already, and he is our contact point to perform adsorption studies. So he tries to adsorb, to check the selectivity when you have mixtures of CO2 and methane, which is a very important mixture to separate for many applications. And to our surprise, we got a factor of 10,000 when you have a diamine like this, which drops to about 1,000 when you have just a secondary amine. And then again, it drops when you have a primary amine. So it seems that the bulkiness of the molecule and the basicity of these amines have a drastic influence on the selectivity towards CO2, okay? But why? Can we understand about atomic level details that can drive this mechanism? So before showing you some NMR spectra, I should tell you that we have to be very rigorous packing our samples, because if you pack the samples in open air, so this is a typical sample holder, which is a rotor which has more or less 1.5 centimeters height and 3.2 to 4 millimeters of diameter, okay? And you just have to pack the powder inside, you close it with a specific cap, and the size, you have the relative size of the rotor by putting a coin just on the side here. And we have built an in situ NMR cell where you can close it with a clamp. We put a cap on the bottom part of a metal piece here, and then we just degas the sample first. Okay, once it is degassed, we can admit any partial pressure of gas that we wish. Okay, we wait for equilibrium to be reached, and then we are ready to mix other gases as well if you want. Okay, so with this done, we just close the cap inside, still with control environment, and then we just run to the NMR magnet to do our analysis. So this NMR cell that you see here on the right then is hooked to this front side here. And of course you have then the nitrogen valve, because if you want to do partial pressures below ambient pressure, then you have to fill it up 1 bar with an inert gas. You have the vacuum pump, and you have then another inlet to add a second gas if you want, or just a mixture of gases. This is a general apparatus. So carbon spectra are as follows. You have now carbon-13 cross-polarization magic angle spinning spectrum. I will not go into details about what does it means, but this is more or less mimics what you have in the solution state NMR. You can see here 2 regions. You see the region of physisorb peaks, which is about 125 ppm, and you have the chemisorb region that are on the left side. Okay, so you can really see how the population of physisorbed and chemisorbed species evolve with different partial pressure of CO2. This was the first publication showing variable pressure NMR, by the way, in the literature. And you can really see that at a very low pressure, depending on the type of amine you use, I just concentrate now on these two amines, primary and secondary. You can see that at very low pressure, this intense peak is populated first, and then the other smaller environments start to populate, okay? And the kinetics of population also changes. I should say that the loading of amines is more or less the same. So we are in conditions that we can compare all this. And the spectra have been normalized. I will not go into details, interesting details here, but I will just skip it for now. So we try then, so from carbon, we just see the peaks, and we have here a huge overlapping of environments, okay? What about trying to extend our vision through the unknown by playing with another dimension, this time the proton dimension, this vertical dimension? We can now see how the spins, they speak with each other, so how they are coupled dipolarly. So if they are close in space, if a carbon is close in space with another proton, you will see a cross peak showing in this map, this contour plot map. So you can see that these three chemisol species, they correlate with basically the same protons, but some difference can be observed here. Okay. Still very complicated to interpret. We have tried other approaches where we, prior to CO2 absorption, we just exchange all the labile protons with heavy water. And then instead of protons, we have the deuterium now. And then after that, we just reabsorb with CO2. And hopefully we see that these protons will disappear from the spectrum. You can see some peaks disappear, which can help us. We have done this systematically for all amines. I will not show you all the amines, of course, but this greatly helped us to really have an unambiguous assignment of certain protons, at least, certain proton environments. Of course, to avoid, far-fetched assignments, we need to couple our experimental data with computational analysis. So we have done several cluster calculations where we have a silica slab, where we optimize the distance between two amines. We have made maximum loading possible, so we assume that the amines are in pairs for these models. We have also done isolated amines, of course, but I will not go into all these details. This is the level of theory we have used for our calculations. And we have done, probably hundreds of calculations, okay? So I will skip it. At the end, the lowest energy models, the three lowest energy models are these ones that are shown, that are depicted in the slide. And I was glad to see that for the species A, calculations came up with the chemical shifts at 4.3, which is exactly the one that disappears upon deuteration. So this is a very labile proton that can be exchanged by deuterium, and this helped us to assign this proton environment. This was very strange because usually carboxylic acid protons, they like to be engaged in hydrogen bonds like the other ones here. But this one is not engaged in hydrogen bonds somehow, okay? It was a bit puzzling at the beginning, but there is no other chance to have this kind of chemical shift if we don't have this proton in this position like that, in this specific arrangement. So as you can see, carbon chemical shifts, they fit quite well the experimental data, okay? And we can even see this peak here, this deshielded peak, which can also be observed in proton-silicon correlation spectra. And this is due to the existence of silanols that have not been grafted. We have some silanols here that can hydrogen bond. So this is also the first proof of hydrogen bonds between the surface walls and the amines that are grafted. So there is still a problem here, an intriguing problem that we can compute this 11.4, about 12 ppm proton chemical shift that is typically a proton that is engaged in this strong hydrogen bond with a neighbor amine. But we could not find a chemical shift about 12, as you can see here, for a primary amine. So then we try to do a two-dimensional spectrum of a secondary amine, this secondary amine, and we can see now we have a peak at 12 ppm. So somehow this is something we can still not explain. Why in hell only secondary amines produce these very strong hydrogen bonds with negative amines. There is no other way to produce this 12 ppm peak. Okay, we must have another negative amines. At least this is an unequivocal proof that you have pairs of amines interacting, which is fun. There's still a problem. What is this peak? Hey, you know, in 2011, I showed you the first work we have done. We only saw 2 peaks, carbamic acid and another one, which we think is the ion pairs, carbamate. But when we control the environment, when we pack the sample, we always have an additional peak that we label here A from now on. And this was very puzzling. We tried to understand what is this peak A, this resonance A. Okay, and there are 2 possibilities. So this is the experimental chemical shift. We went through the models, and the only way to get a calculated carbon chemical shift that comes close to this experimental one is when we have these 2 models here, these 2 DFT models. So one is when you have a free OH, and the other oxygen is now hydrogen bonded with a negative amine. And the other situation is when you don't have any pair of amines, you just have an isolated amine, which is hydrogen bonded to local silanols. Okay. Which one is the right model to describe our experiment? This is the question. So to try to disentangle this problem, we try to, apart from the conventional grafting, okay, you just graft amine and then you adsorb CO2 and that's it. We try to protect these amines prior to grafting. Then we graft them because it's very bulky. They will be spaced apart. So the idea here is try to control the amine aggregation. Okay, try to put them further apart as much as possible to quench amine interactions. These strong hydrogen bonds. So at least we want to minimize them. Okay, so we have done so. This is easily removed by just heating. You can regenerate the initial amines. Now they are further apart enough so they cannot interact. And then you reabsorb again CO2. And here are our CO2 species. So we are the master students that has, done all this work. So she has done grafting in a conventional way, putting as much amine as possible with a very high loading, 2.8 millimole per gram. Then we try to dilute more or less 3 times. And we see that the spectrum changes like that. You see that as you dilute the amine coverage, you start to favor the intensity of resonance A. With our approach, where you add a bulky spacer, you can now really reverse these intensities from here to here. Now A is the one that dominates completely. So these lead us to think that A must be an isolated amine, because you are favoring isolated amines when you do this transformation of your surface. Okay, so based on these experiments, we can discard this model here, and we are pretty much sure that we have an isolated amine that is hydrogen bonded to the walls of the material. Another problem is to really prove if this intense peak C is a hydrogen bonded, a neutral hydrogen bonded carbamic acid, or just an ion pair where the proton has been transferred to the negative amine, or maybe could also be a zwitterionic entity. This is tough to prove. We tried to use a different technique. In NMR, you need to put the powder in the sample, as I said, and you need to spin the rotor. This is something I didn't say. When you spin the sample, if you don't spin the sample, maybe it's better to start like that. 0 kilohertz, you have a powder average, so you have a powder pattern. Okay, so in NMR, molecules are not tumbling like in the liquid, so you have zillions of different orientations. So the chemical shift doesn't only depend on the chemical environment of a given nucleus, but also on the orientation of the electronic electron cloud with respect to the magnetic field. So we call these chemical shift anisotropy. These will lead to a distribution of chemical shifts. And if you sum up all these statistics of chemical shifts, you end up with this probability curve, let's call it like that. So you can get rid of this to try to mimic the tumbling of molecules in a solution. The way you do it is magic angle spinning. And you spin as fast as you can, so you can average out this interaction. So you can now spin rotors up to 110 kilohertz. We will not see any spinning segments, okay? So you are left with only a single peak if you go to infinite speeds, okay? And that's how you get your isotropic chemical shifts. But keeping our anisotropic chemical shift is also, it's nice because we have additional information that we may not have, we cannot access in solution. So this is not completely useless, this anisotropic interaction. In fact, using a simple language, I don't want to complicate the story, you have these particular shapes, these funny shapes that have a singularity and various shoulders. And basically, you may have, by fitting these broad peaks, you can obtain three additional chemical shifts, let's call it like this. So in total, you may access 4 chemical shifts, okay? I'm abusing a bit from NMR language. I hope there is not an expert in the community. But basically, these sigma 1, 1, 2, 2, and 3, 3 are the principal components of a tensor. So interactions in NMR, in associated NMR, are defined as tensors, okay? So because of the tensorial nature of the interactions, you have these funny shapes. Okay, so we try to make an effort to be on particular pressures, partial pressures, to favor the intensity of one of the species. So if you go very low in CO2 pressures, you mostly favor an intensity of C, okay? And then you spin the rotor very slow intentionally, and you get the spectrum, which has a nice chemical shift anisotropy envelope, and you can just fit it and get these principal values of the tensor. And this will tell you about the chemical shift anisotropy tensor is very sensitive to the proton transfer. This is well known in the study of peptides and amino acids, okay? I just took inspiration from these papers and just transported that idea to this one, to these materials. And as you can see, I just start from our models, and I try to compute the principal components of the CSA tensor, okay? And they are here overlapped in dashed lines. And this is the experimental one. As you see, the fit is not bad, okay? Starting from models from something that is not crystalline, okay? You should not forget that I don't have a C file. I don't have any database to look for a crystal structure. So these are imagined cluster structures where we try to optimize then these surface molecules. And it's pretty good for what it is. We went to a database where we have neutral amino acids and also zwitterionic amino acids. And we try to put the principal components in this plot, okay? So in the y-axis, we just did a linear combination of these principal values of the tensor in a way so we can distinguish better the small differences, okay? And here I just choose one of the principal components of the tensor, the one that maximizes differences between protonated and non-protonated amines. So just to be simpler to understand, you have in squares the experimental value, and in circles the calculated value. As you see, it fits quite well, in fact. And this corresponds to a proton that has jumped from the carbamic acid to a neighbor amine, okay? Usually, your experimental value and should fall in these zwitterionic amino acids, okay? When you're neutral amino acids where the proton has not jumped to a neighbor amine, you might have an intermediate case where he's almost jumping, but you have just a strongly polarized hydrogen bond, and one that is not so strongly polarized. And you see that the CSA is extremely sensitive to the degree of polarization of this OH bond. And when it jumps completely, you see that the singularity changes quite a bit from the previous one. So we have here an NMR technique that can sense proton transfer. So the last problem I want to present you is about the effect of moisture. You know, lots of work done in MOFs, COFs, zeolites for CO2 capture concentrate on pure CO2, but pure CO2 doesn't exist in any source. You have CO2 is always mixed with something else, okay? And water is almost present in every gas mixture and is a big problem. So there was a paper stating that there was a dramatic CO2 uptake when moisture is in wet samples. So we try to understand why. When we read the paper, the explanation was that carbonates that are formed when you absorb CO2 in these materials then become bicarbonates once you put water, which makes sense. And then it increases the CO2 capture capability because the stoichiometry changes and you can now accommodate 2 times more CO2. But when you compare the isotherms of dried samples and previously absorbed and samples that has been exposed previously to water and then to CO2, we see that the isotherms, they overlap. We don't see much changes here. So we have tried to do some NMR on that. The dry samples are the typical spectra that we have seen before, A, B, C. Once you just expose with moisture, you get with very low amount of moisture, in fact, is almost nothing. A peak disappears completely. And you have basically a conversion of this B species, which is carbomic acid, to the ion pair, okay? So we try to understand if this could be bicarbonate, which is overlapping these bands. This could be. So we have tried to do carbon NMR of a tertiary amine, which cannot form carbamates or carbonic acid at all, can only form bicarbonates. So, and the result is the following. So this is now tertiary amine. And tertiary amine just fall at 161 ppms. So it is definitely not bicarbonate, this species here. So how we work, redefine the mechanism, and what happens in fact is that carbonic acid is converted into ion pairs and not necessarily the formation of bicarbonates. And we have computed all this. We have tried to calculate Gibbs energies of all these species. What happened is that the A species, which is isolated, when water approaches these surface amines, it hydrogen bonds like here, and then the peak shifts from 155 or 153 to 161. So it becomes this A prime peak here. At the same time, carbonic acid is transformed in these ion pairs. So basically the proton just jumps to the neighbor amine, and water is the shuttler of this proton transfer. Okay, water just promotes this. This is well known in proteins, for example. We have tried also to do the same in tertiary amines, where we put moisture in tertiary amines, and we see now there is a difference if you have the isotherms of dry samples and you expose previously to water before absorbing with CO2, you see now an enhancement of CO2 capture. And you see the peak always increasing. That proves that you really have an enhancement of an increase of CO2 species that are formed in the pores. We were curious about this peak forming 155 ppm because we cannot form any carbonic acid. We assigned previously this 150 something ppm peak to an isolated carbonic acid. And we see it again, but in a tertiary amine. And it appears that we can form, in fact, a quaternary amine, which was never claimed before. But we could also form a zwitterionic species, okay? But the chemical shift is much lower than this one, so we can just discard it.
Dear Luis, we need to speed up. We are almost.
I still have 3 minutes, I think, isn't it?
Okay, it was 40 minutes.
Oh yes, 40 minutes. So I'm gonna finish with this. So just to wrap up, this is the last slide. I showed you that with two-dimensional experiments, we can have a better assignment of these surface species. We can couple these with calculations and at least assign 3 different chemisort species. We can use chemical shift anisotropy to demonstrate proton transfer in our surfaces. And we can also monitor identified moisture-induced CO2 capture, CO2 species. So with this, I will probably postpone. I have some future prospects, but I will go immediately to the slide of So I would like to thank the funding agencies and all my team and collaborators and all of you for listening to my talk. Thank you very much.
Many thanks, Dr. Luis. I'm sorry for having interrupted your presentation. It was being very interesting. And, it is a topic where you showed this coupling of the NMR technique with modeling, and we can explain very, very detailed this carbon dioxide mechanism over these materials. We have time for one question because we are accumulating delays. I'm asking to the people inside the room if there is any question you want to ask, because I think from YouTube there is no question. And if not, I can ask you a question related with carbon dioxide desorption. So you explained quite clearly this mechanism of absorption, and regarding the capacity of the absorbent to be involved in absorption and adsorption cycles. What can you tell us about the mechanisms of dissorption and how these anions are then stable over these cycles, absorption and dissorption?
Yeah, this is a very complex problem. I avoided to go into that because of time restraints, but basically I can show you one slide. So when you absorb, you have certain mechanisms like this one that are inspired on solution amines, and people, what they do, they transport all these solutions to the solids, okay, without much proof. And what happens is once you absorb CO2, this amine, for example, you have many routes. You can go to intermediates, isocyanate intermediates with dehydration, or you can go and put a second amine interacting, and with further dehydration, you can form urea. Once you form urea, these molecules are very stable, and you deactivate the material basically. But is it true that it's urea that is formed? There is no unambiguous proof of the formation of these. We may have other molecules forming. Also, you may regenerate material with temperature. If you increase temperature too much, you risk to degrade your amine, also which are organic materials. So you need to be, on the safe side. If the chemical bond between CO2 and amine is too strong, in other words, if the absorption enthalpy is too big, you may not be able to regenerate, to degas, to desorb the molecule unless you heat to very high temperatures and you risk degradation. Or
thermal
kinetics is very high. So you need to play. It's an interplay between different variables: absorption kinetics, absorption capacity, stability of the adducts formed. It's very complicated. So we try to make sense of all this, making small variations of the chemistry. Trying to quench intermolecular interactions, trying to favor them, trying capping mechanisms, trying labeling schemes, and trying to disentangle the different contributions so we can have an overall picture about what happens.
That's interesting. We have a lot of studies to be done in this subject yet. We thank you again for your presence, and we will move for the next presentation. And for that, I will pass the word to my colleague, Dr. José Luis. Here's the question. Thank you.
Hello, good afternoon. Thank you very much for your introduction, Professor. As we have some delay, I quickly present the following presentation, entitled Synthesis and Characterization of Novel Ionic Liquids, crystal-based on substitute pyridium cations, that will be presented by Andrea Filipa Magalhães de Isas Lopes dos Santos, da Universidade Nova de Lisboa. So please, Andrea, when you can start.
Good morning, everyone. My name is Andrea. I'm a PhD student, and today I'm going to talk a little bit about my work, synthesis and characterization of novel ionic liquid crystals based on substituted pyridinium cations. So what are ionic liquids? Ionic liquids are organic salts with low melting point, normally below than 100, and they are made by a combination of organic cations and anions that can be organic or inorganic. They have peculiar properties such as high thermal and chemical stability, high ionic conductivity, reduced vapor pressure, and the most interesting one is that depending on the cation and anion selected, the physical and chemical properties of the final ionic liquid crystal, the ionic liquid can be modulated. Ionic liquids can be applied in several fields, such as separation media, electrolytes, working fluids, green solvents, and in advanced materials, which include liquid crystals displays. So the first liquid crystal was reported in 1888 when it was observed that when cold-steel benzoate starts to melt, it first became a cloud liquid and then clear up upon heating. In fact, a liquid crystal is a mesophase between the solid phase and isotropic liquid phase, and in this phase the molecular mobility is increased and the material turns fluidic or plastic. This behavior can be promoted by mesogenic groups such as aromatic rings. Liquid crystals can be classified in order of their thermodynamic genesis, and if the mesophase is thermotropic, it means that the liquid crystalline phase is achieved when the temperature increases and the pressure and concentration remains constant. If the material is monotropic, the reverse phenomenon is not observed. They also can be classified in order of their constituent molecules, and if the molecule is elongated, it is called calamitic. If the molecule has a shape of a disc, it is called discotic, and if the molecule has a shape of a banana, it is called banana. They are made by a central rigid core, normally aromatic, and a flexible tail, often aliphatic groups. They also can be classified in order of their molecular arrangement, being nematic and sematic, the two most common ones. In the case of the sematic, they are also called lamellar liquid crystalline phases, as the molecules are arranged in layers. Liquid crystals can be applied in several fields, such as medical thermography, liquid crystal lenses, drug delivery, display devices, among others. So the main objective of my work is to combine the properties of ionic liquid to the properties of a liquid crystal to create a new functional ionic liquid crystal. Most of ionic liquid crystals reported are based on methylimidazole cations. So in our work, we tried to develop ionic liquid crystals based on pyridinium and methylpyridinium cations. In order to study the presence and the location of the methyl group, 3 different compounds were prepared, the 2-picolinium, 3-picolinium, and 4-picolinium. In all cases, it was substituted with long alkyl chain, .sil in our case, because it is known that chains between C10 and C18 are able to promote the liquid crystalline behavior, and because we are only interested to study the liquid crystalline behavior of the cation, in all cases, bromide was selected as an anion. All prepared compounds were characterized by first NMR, FTIR, and elemental analysis in order to confirm the chemical structure, and then by DSC, POM, and X-ray diffraction in order to study the liquid crystalline behavior. So to prepare the ionic liquid crystals, two synthesis methods were compared. The first one, the conventional method, we are limited by the boiling point of the solvent, in our case acetylnitrile, and therefore 80 degrees. The reaction time is between 24 and 48 hours, when for the case of microwave assisted reaction, no solvent is needed. The reaction time is 35 minutes and the yields are high. This means that microwave assisted reaction is a more efficient, greener, and faster process. All prepared compounds were characterized by proton and carbon NMR, FTIR, elemental analysis in order to confirm the desired chemical structure. In order to study the liquid crystalline behavior of all ionic liquid crystals prepared, DSC and PYCHEM analyses were performed. And for the case of C12 pyridinium bromide, by the first cycle, the material is crystal when prepared, and in the second heating, 3 different liquid crystalline transitions were detected. The first one at 25 degrees, the second one at 35 degrees, and the third one at 60 degrees. The isotropization was at 124 degrees. For C12 2-picolinium bromide, by the first cycle, the first heating cycle, the material is crystal when prepared, and in the second heating, 2 different LC transitions with low enthalpy were detected. The first one at 25 degrees and the second one at 75. The isotropization was at 124 degrees. For C12 3-picolinium bromide, by the first cycle, the material is a mixture between crystal and liquid crystal when prepared, having focal conicals detected by PYCHEM, which are characteristic of asthmatic phase, and in the second heating, 1 transition was detected, having a small liquid crystalline window. For C12 4-picolinium bromide, as the previous material by the first cycle is a mixture between crystal and liquid crystal when prepared, having focal conicals detected by PYCHEM, and in the second heating, only 1 LC transition was detected with a small LC window. The isotropization is at 70 degrees. In order to compare the thermal behavior of all ionic liquid crystals prepared, in the left figure is included the second heating runs for each material, and it's possible to observe that C12 pyridinium bromide is the one that exhibits more liquid crystalline transitions, having 3. It also has a large LC window, and for the case of C12 2-picolinium bromide, it has 2 LC transitions and also a large LC window. For C12 3-picolinium bromide and C12 4-picolinium bromide, only 1 LC was detected with a small LC window. It is possible to observe that the position of the methyl group impact the position of the isotropization, decreasing between 124 to 70 degrees. In order to understand what happened to the LC behavior after successive heating runs, in the right figure is included the 4 heating runs for each material, and it's possible to observe that C12 pyridinium bromide preserves its mesomorphic behavior, as it is possible to detect the same 3 transitions even though these 2 are not completely deconvoluted. However, for C12 2-picolinium bromide, the material turns monotropic on cooling, meaning that this transition is between a crystal and isotropic liquid. For C12 3-picolinium bromide and C12 4-picolinium bromide, both compounds convert into a non-mesomorphic materials. In order to characterize which mesophase is presented in each material, X-ray diffraction studies were performed. And for C12 pyridinium bromide was detected possibly 3 different liquid crystals, being S1 and S2 symmetric with structure layers, as it is possible to detect a strong intense peak at small scattering angles and low intense peaks at large scattering angles. It was also detect asthmatic A, which is asthmatic with disordered layers, as it was possible to observe only the large peak, the intense peak at small scattering angles. For the case of C12 2-picolinium bromide, two different liquid crystals were detected, being both asthmatics with structured layers. And for the case of C12 3-picolinium bromide and C12 4-picolinium bromide, only one liquid crystal was detected, and in both cases is asthmatic A, which is asthmatic with disordered layers. So to conclude, all prepared ionic liquid crystals were detailed characterized by spectroscopy, thermal, and microscopic analysis. Pyridinium and picolinium ionic liquid crystals exhibit asthmatic phases. A small modification at molecular level provokes significantly impact in their crystalline behavior. Moreover, new promissory materials based on ionic liquid crystals have been developed in order to apply them in the future applications in display devices. Finally, I would like to thank to my supervisors and to Professor João Figueirinhas for all the help and support during this work, and also would like to thank to the institutions for the financial support, and of course to you for your kind attention. Thank you.
Thank you very much, Andrea. Thank you very much to take the time that you have. We don't have any question yet in YouTube. We have only a little bit time. So let me do only one question at the moment. I'd like to know why are so interesting these novel ionic crystal liquids that you prepare. So I mean, which application they have? They are, well, yes, which application they have, please.
So these materials is working as a first starting point to understand which one is the best, and then to apply them in display devices for chromogenic materials, for example.
Sorry?
I say that these materials work as first to so first we try to understand which liquid crystal prepared who is the best one, which has the most LCM transitions, and then what are the difference between them, and then we will choose some of them to apply them. We'll change the anion to create a new functional material. This is like the starting point.
Okay. Thank you very much, Andrea. Thank you very much for your presentation. Maybe at the end of this season, if we have more questions, we can call you to reply. Okay.
Okay.
So thank you very much. So the following presentation entitled Purpural Selective Reduction by Titanium Oxide Sensitized Photocatalysis will be presented by Joana Carvalho Lopes from the Faculdade de Engenharia da Universidade do Porto. So, Joana, when you are prepared, please.
Hello, good morning, everyone. I will present my work by furfural selective reduction by titanium dioxide as photocatalyst. This work was developed in the University of Porto in the Associated Laboratory LSRE LCM. To begin, I will start my presentation talking about biomass valorization and use of furfural as protoform compound. Next, I will talk about heterogeneous photocatalysis and use of titanium dioxide as photocatalyst. I will show my photocatalytic results, namely the characterization of catalysts and their application in photocatalytic reduction of furfural to furfuryl alcohol. And finally, I will present my main conclusions of my work. Biomass, how everyone knows, biomass is an ideal alternative for traditional fossil resource due to its abundance and environmental friendly. More specifically, lignocellulosic biomass is a potential organic carbon source that is abundant in agricultural residues. Lignocellulosic biomass is composed for 3 different units. The more abundant is cellulose. Cellulose is present in 40 and 50% in all composition of lignocellulosic biomass. Cellulose can be converted by gasification in order to produce biogas, such as hydrogen. Also can be suffer pyrolysis to produce bio-oils, such as ethanol and butanol, but also can suffer hydrolysis to produce biochemicals. Normal hydrolysis of cellulose involves the use of high temperature, high pressure, and metal catalyst. However, with hydrolysis, you can produce several important compounds, such aromatic compounds, aliphatic, hydrocarbons, and sugars. In the family of sugars, I will talk about furfural. Why? Because furfural is a promising renewable platform compound. Using furfural, furfural is a building block for the synthesis of a wide range of value-added organic compounds, namely to produce furan, cyclopentone, methylfuran, and furfuryl alcohol. The conversion of furfural into furfuryl alcohol is an important reaction and has attracted much attention. Since furfuryl alcohol is a raw material used for the production of several resins, flavors, biofuels, pharmaceuticals, and others. However, the industrial process to convert furfural normally require operation conditions under high temperature, high pressure, and use of metal catalysts. More specifically, the conversion of furfural using a liquid phase dehydrogenation to produce furfuryl alcohol involves the use of catalysts based on copper, temperatures around 20 and 200 degrees, and hydrogen under high pressure. These reaction conditions are not favorable and are not environmentally friendly. For that, it's very important to develop a new alternative route. For that, I talk about photocatalysis. Photocatalysis is alternative for this synthesis, since it's possible to operate under moderate condition of temperature and pressure. It's possible to recycle and reuse the catalyst, and photocatalysis is a process activated by light. In this case, we can use natural light such as sunlight, but we also can use artificial light such as LEDs that have a low consumption of energy. In this way, I present here a simple mechanism of photocatalysis. In photocatalysis, we have an optical semiconductor that is photoexcited by radiation, promoting the transferring of electrons to the conduction band and the formation of holes in the valence band. When we have favorable conditions, these reactive species are transferring for the surface of semiconductors, allowing the reduction and the oxidation of substrates. In this case, we're allowing the reduction of furfural in order to produce furfuryl alcohol. In photocatalysis, it's very important to choose a photocatalyst. In this way, I talk about titanium dioxide. It's a benchmark photocatalyst, and it is used in much areas and presents great activity in some of them. However, titanium dioxide is a metallic oxide activated by UV radiation. However, present a high chemical stability and present a high oxidation potential on valence and band holes. There are many ways to synthesize titanium dioxide. In this work, I used a social method synthesis. It's a simple and easy method that normally involves the synthesis of a social precursor that suffer a calcination in order to form the crystalline phase. In this work, I use different temperature, the temperature of calcination between 400 degrees and 1000 degrees. I start in 4000 degrees because is the temperature necessary to overcome the amorphous phase of the material. And the objective of this variation of the calcination temperature is to understand how the crystalline phase will change, how the anatase phase will change, and rutile. In this way, some characterization was done to synthesize the titanium dioxide. First of all, I start doing the morphology of the material by SEM. In this image is represented material calcinated at 400 degrees. It's visible and is observed that this material have small particles with a spheric form. With increase of temperature to 600 degrees, it's visible that particle size increase and the shape is different. And when you look to the image, same image with of the material calcined at 1000 degrees, it's obvious that particle size increase and shape is very different compared with first one. In addition to the morphology, the optical properties of the material was also analyzed. In this image is present the band gap, the top plot of the different materials, and in this table is presented the value of band gap of different materials. Looking for the image, it's possible to see that material calcined at lowest temperature, 400 degrees is the black line. We have a band gap of 3.50. When we change calcination temperature, the material changes band gap. And looking, for example, for the material, the green line, looking for the material calcined at 1000 degrees, the band gap is 2.96. With this analysis, we can conclude that with increase of calcination temperature, the band gap of material change and decrease. This can be related with increase of calcination temperature, the crystallinity of the material and particle size increase, and this way it can result a lower rate of electron-hole combination that will be affect the photocatalytic activity of the material. Moreover, to define the fast transition of titanium dioxide, it was done X-ray diffraction. In this graph is present the diffraction peaks of anatase and rutyl phase, and the black line presents material calcined at 400 degrees, and to hope is higher temperature. Looking for this peak is representative of anatase phase, and you can see that the peak is bigger to lowest temperature. The same happened here, and in the case of rutyl, the contrary happened. The material calcined at highest temperature present a higher peak. The same happened here. With this information, we can calculate the quantity of anatase and rutyl present in the samples, and we can observe that the material calcined at 400 and 500 degrees contain 100% of anatase. The transition phase occurs between 500 and 600, and we can conclude that with increase of calcination temperature, the anatase phase decrease and rutyl phase increase. This difference of phase will in fact affect the photocatalytic activity of the material. All the synthesized materials was tested in the photocatalytic conversion of furfural into furfuryl alcohol. In this case, it was used a batch system with refrigeration in order to maintain the ambient temperature. It was used for OV LEDs, and it was used organic solvents and anaerobic conditions. To initiate this study, it was studied the effect of solvent in this reaction. It was evaluated during the reactions. It was taken samples and will be analyzed in HPLC, and the results are presented in this graph in 3 different parameters: conversion, selectivity, and yield after 20 minutes of reaction. When water is used as a solvent, I don't see the formation of furfuryl alcohol. In the case of when it was used acetonitrile as solvent, the production of furfuryl alcohol is very low. When it was used as alcohol as solvent, the photocatalytic activity is very higher, and ethanol is the best option for the use of solvents. After select the best solvent, all the photocatalysts was tested, and the results are presented in this image. It represents the concentration of furfuryl alcohol during the time, and you can see that the red line presents material calcined at 600 degrees that present the best photocatalytic activity. In this way, you can conclude that all the characteristics of the material is the best for this reaction. In the case of the material calcined at 400 and 500 degrees is the next one to be the best in photocatalytic activity, which indicate that anatase is the best for this reaction, but we need to contain a quantity of rutyl. In this way, with this work, I can conclude that anatase anatase phase contribute positively for the photocatalytic activity of the material. The increase of calcination temperature promote the increase of particle size and decrease of band gap of material. After 20 minutes of reaction, the best efficiency of sulfuric alcohol was found using ethanol as solvent, reaching 95% of yield in the production of sulfuric alcohol, and high photocatalytic activity. It was obtained using the titanium dioxide calcinate at 600 degrees. Thank you all. Thank you all for financial support, and thank you all for kind attention.
Thank you very much, Joanna. We don't have any questions yet in YouTube, and as we have some delay, we leave all the questions to the end of the season. So,
may I make a question?
Of course, yes. Well,
yes. Joanna, it was a very nice work and a very nice presentation. I have some questions, some curiosity, let's say like that, regarding the results. So, best material you have found, and the synthetic materials you did, it contains rutile and anatase, correct?
Mm-hmm. Yes.
Yes, because only rutile was not giving good results, and anatase was giving fair results, and the presence of rutile acts like a promoter. You can explain that?
I can explain that anatase, only anatase have a good activity in this case because of mechanism of anatase that will promote the formation of radicals and the mechanism of the reaction. In this case, the rutile will improve these results. I'm studying this case. I'm studying, but I think that the promote between the anatase and rutile will be the best options. I don't know if.
Okay, sure. Some more studies are needed, but just one final question, very quick. You compared your materials with commercial titanium dioxide.
Yes. Yes, I compare.
And
the commercial titanium dioxide is P25 have the different quantity of anatase rutile that I'm obtained. Is the reason that I not represent because I don't have I can say at 600 degrees with the calcination at 600 degrees, I have the same quantity of the anatase and rutile. But with the commercial, I have a small difference and a better activity. But in this work, my main objective is understand how anatase and rutile will influence my mechanism, my reaction mechanism.
Thank you for the time, Jose.
Thank you very much. The last presentation, I think that the speaker cannot do presentation, so we will play a video. The presentation has the title Novel Bio-Based Epoxy from Epoxidized Vegetable Oils by Marius Stelian Pogba from the National Institute of PYCHeM from Bucharest. So,
thank you for the introduction, and sorry for this, but yeah, I'm not feeling the best. I will share my presentation. Can you see it?
yes, we can.
Okay.
Hello, my name is Marius, and today I will briefly talk to you about novel.
Marius, you have to turn off your mic.
Oh, sorry.
Hello, my name is Marius, and today I will briefly talk to you about novel bio-based epoxies from epoxidized vegetable oils. Linseed oil in its native form presents double bonds on the backbone, which give it drying properties, meaning it can cross-link in air, opening up possible applications as finishing touch on woodwork, electronic insulating adhesives, or other general adhesives. By applying a mild oxidation reaction, we can obtain epoxy rings on the double bonds before, opening up more possible exploitations. For this, we used an epoxidized linseed oil and a commercial hardener, here Epilox hardener H1030, which is a mixture of primary, secondary, and tertiary amines, also containing catalysts and accelerators. We reacted these two and obtained cross-linked epoxy resins. For this, we used a 2 ELO to 1 hardener weight ratios under different working conditions presented here in the table on the right side. And finally, we wanted to see the influence of different cellulosic components, microcrystalline cellulose, MC, and plum seed cellulose, SC, in low weight percentages on the different properties of our final products. Firstly, we investigated the consummation of the reagents and the finalization of the reaction by FTIR spectra. We can find the expected characteristic bands for esteric carbonylic stretching, epoxy ring symmetric and asymmetric stretching, and also scissoring of the epoxy ring here, and here. If we look on the hardener side, it being a mixture of different compounds doesn't help with the interpretation, but we can find the general ranges for different compounds here. By investigating the cross-linked materials, we can find that after the reaction, the hydrogen-bonded hydroxylic groups can be found here, and also we can find some residual epoxy ring stretchings, scissorings, and also the hardener nitrogen containing here. By the addition of the cellulosic components, we can find that they have increased all of our peaks intensities, but more importantly, the polar ones here at the OH and also here at the NH, NH2, etc. This means that the surface will have a higher polarity, which will be presented at further slides. But we investigated the thermal stability of our materials, and as we can see, harsher thermal programs will lead to a shifting of both maximum degradation rates towards higher values. More cross-linking time will lead also to a better thermal stability by shifting these two peaks towards also higher values. The addition of the cellulose shows the reinforcing effect of it by also shifting these two thermal degradation rates towards higher values. On the thermomechanical behavior, we can see that higher thermal programs will lead to more flexible materials and the longer reaction times will lead to stiffer materials. The addition of cellulosic compounds will lead to increased stiffness in our materials. For the surface morphology, we can see that unfilled epoxy resins present some small air bubbles evenly distributed on the surface. But after the addition of microcrystalline cellulose, we can see that it bundles up in different morphologies, which bring with themselves increased air pockets, which will be detrimental to our final properties. But by the addition of plum seed cellulose, we can see that it distributes evenly on the surface. As I said before, on the FTIR spectra, the addition of cellulosic components increases the polarity of the surface and thus increasing the hydrophilicity. This is proven by the slight lowering of the water contact angles. And as conclusions, we have successfully obtained flexible epoxy resins from epoxidized linseed oil. We have shown the completion of the cross-linking reaction by FTIR, and also we have investigated the thermal behavior by TGA. After the addition of only 0.5% of cellulose modifiers, we have shown that the thermal stability was increased, and also we have proved the reinforcing effect of the cellulose on our epoxy systems. Also, the addition of cellulose increased the polarity of the surface, increasing its hydrophilicity. Overall, we have shown that we can obtain bio-based epoxy systems using an epoxidized linseed oil and a commercial petroleum-derived hardener as alternatives on other classical epoxy systems. And if you have any questions, please be free to ask them, and thank you for your attention.
Thank you very much, Marius, to share the video of your presentation of your work. I don't know if you are in conditions to answer some questions. Do you feel right to answer something?
The second COVID shot has done a deal on me, but hopefully I could answer some questions.
Well, let me do only one question. The work is really interesting about the bio-based epoxy materials. I'd like to know if the properties are compared to commercial epoxy, so they could be used in real applications.
The idea is the project is currently in its first steps, and we only obtained the epoxy systems derived from this linseed oil. In the next step, we already have the protocols to compare to a classical epoxy system to see the influence of the flexible part here, the flexible part being the resin itself. So yes, it is in our plan.
Okay, thank you very much, Marius. Thanks. I'm sorry to ask in these conditions that you have. You are. Well, we don't have any other questions, I think so. Professor Le has to
Yes, we have
something.
One question that
Okay.
is arriving from the audience. We would like to know what is the average transmittance value in the visible range. I'm just translating the question, so I hope Marius understood the question. Marius, did you heard the question? What is the average transmittance value in the visible range? That was the question placed.
What is the, could you repeat it, please?
What is the average transmittance value in the visible range? I'm just reading, I cannot explain it better. This question.
Oh, you mean a UV experiment, a UV analysis?
I suppose, yes. It's not me asking. It's
It
Anna.
should, let me, it should be in the yellow region because the resin is yellow. I don't think I understood the question correctly.
Yes, and I cannot also help because only with interaction with Anna you would be able to solve. So you answered. So we hope that you answered correctly. Thank you.
Thank you too.
And I think we finished this session. We will continue in the afternoon. So it was good to have you here, and we will continue. I don't know if Ines wants to close.
Yeah, thank you. Thank you so much, all of you, for the presentations. It was very good to hear all of your work. Congratulations to the presenters. Thank you also to the chairs of these sessions, Professor Elder and Dr. José Trivino. Thank you so much. For the remaining of you that are seeing us in YouTube, thank you so much for watching, and we will come back at 2:30. Thank you so much. See you. Bye.
Bye.